Hi, Zheng, how are you? Good morning.
Hi, how are you? Can you hear me?
Yes, I can hear you well.
Okay, thank you.
Since you opened the room, you're the moderator now. So if you could make me moderator too, so how it works is
How
you
do I do that? Should
so you
I just quit first? Maybe it's
oh no,
easier.
it's fine. So you click on my profile picture, like on the icon, and then on the bottom there should be an option, make moderator.
Okay, make a model.
Perfect. Yeah, now I will
Okay,
add
good.
the topics and things like that. So everything seems to be working fine. So
Okay.
perfect.
And you will upload the slides or
Yeah, yeah, I'm doing it
okay.
in a second. I'm trying to find appropriate topics. There. Okay, and now the slides. Thank you so much for doing this. Really appreciate it. I hope you had a good day so far and
Yeah, it's
Happy
good.
New Year.
Thank you. Yeah.
Did you mm, did you usually travel for your New Year? Or you
No, really, because usually the Chinese New Year is always during the week or during work weeks, so we usually just get together with friends and have a nice dinner. And so,
nice? It sounds nice. Yeah, we also for the holidays we celebrate. We usually stay and celebrate with friends because it's a little bit expensive and stressful to travel during the holidays.
yeah, that's fine.
I think there's so much more money
Yeah.
to
So,
go.
yeah.
You can go 3 times. Okay, now I'll share on Twitter that we are about to start. Yeah, we still have like around 6 minutes, so you can relax in the meantime.
Sure. So the society, the clubhouse, is it like in the most of the people in the U.S. or actually also outside? What are the how do you what are the memberships?
Yeah, also outside, really all over the world, we have, of course, in the US, on the West Coast, it's right now it's a little bit early for the West Coast, so they will listen to the replay. And then we also have people in Australia and also in Asia, Japan, also and and then in Europe, and then we also had people, yeah, from all over the world presenting here. Um, so
Okay,
yeah,
great.
it's really just very hard to find a time that works for a
For
lot
it.
of people and then works for our work schedule. So that's why we do the recordings. Um, the good thing is that people have the access to the links and the chat and resources we share in the chat. Like later on, we still they'll stay active in the recording. So it's really not a big difference. Just people cannot ask personally a question, but other than that,
Mm-hmm.
it's a very similar experience.
Sure. And how do you try to find a topic? For example, what do you actually do to say, okay, these are the topics seems interest for the club? How do you actually find those topics? Do you actively go out in certain categories, or it's just kind of a random work? What's interesting, you just look up and invite the people, or you actually have a set of say, okay, this month we are trying to do this topic. What do you do?
Oh, yeah, no, it's not by month which topic we do. I just try to be broad. Like, I usually read broadly in science. Like, I think it's really interesting to also read topics that are not my field. And so I try to have a mix of topics. And I also try to have a mix of people where they come from. It's still mostly US and Europe, but yeah, I try to invite people from all over the world. So, but no, yeah, and Australia. It depends how open people are to experience like a new type of presenting and using a different app. And I feel like that most of the time people from the US and Australia and so on tend to say yes, oh, I'll try it, then
Yeah,
than people from other places.
sure.
But, yeah, but we had people also um, from Africa here and so on. So yeah, we try. And from India last week, we used to have more people also from Russia and China, but I think it's not allowed right now. Like this app doesn't exist. So either people use VPN or they can't come here. And then there's also a way to do this on Twitter, but it's the same issue. So that's kind of sad because there are a lot of really great publications coming out, especially out of China. Very interesting work, but yeah, it doesn't work right now. I would have to maybe record it and then stream it, but that's not the same thing. So,
Yeah, it's not. No.
so yeah, we are almost there. 2 minutes left.
So,
I know Frank wanted to. I'm not sure if he will be able to come, but he wanted to come. And yeah, he says it's a little bit late for him, but he will listen to the replay. So
okay, sure.
I used to live in Stony Brook for a while, so I was really close to your lab.
Oh, okay. Yeah, I live in Port Jeff, so it's very
Oh,
close.
nice. Yeah, Port Jeff is really nice.
Yeah. So it's nice during pandemic. I always like every day I can walk to the hub and come back, and so it's good
Yeah,
exercise and nice view.
and they didn't close it, right? Where we lived, they decided they closed here in the city. They closed the parks.
No, the parks are all open. So.
Yeah, that was sad when they closed the parks. I mean, you could still walk on the street, but also not with many people. Like you can like meet with other people and walk on the street. You would have to just with your family or by yourself. But yeah, I like Port Jeff very much. I know one friend of ours, like we are friends with the family, Wang Kan. I don't know if he's at the Brookhaven. He's a physicist in Brookhaven, where you are. Wang Kan. I don't know if you know him, but yeah.
No, yeah, okay.
it's probably big. So it's time to start. So welcome everyone to Science Society, and of course, a special welcome to you, Zhangbu. And I hope I'm saying your name right, but correct me.
Perfect.
No, thank you. And so that the audience gets to know you a little bit better, I will start with a short introduction and a short interview, and then we'll go from there. So, Dr. Zhangmu Chu, he earned his bachelor's in physics in 1994 from the University of Science and Technology in China, and then he did his PhD at Yale University on research he did at Brookhaven's alternating gradient synchrotron. And then he stayed on as a postdoctoral researcher at Yale. And then later he joined the Brookhaven lab as an assistant physicist in the STAR collaboration. And he was then promoted in 2003. And Dr. Shu has co-convened a STAR physics working group studying the chemical and thermal properties of the dense matter formed at RHIC, and a cross-collaboration working group on electromagnetic probes with the upcoming upgrades. Um, so, I assume that you received the funding to build a newer, bigger collider. Is that correct, or is it
So,
still open?
yeah, over the years, the rig, which is we call it relativistic heavy ion collider, has upgrades. We get funding as a collaboration for the upgrades over the years, and now the rig is planned to be shut down in 2025. We are turning into, instead of ion-ion collider, going to turn into an electron-ion collider. So that's roughly the progress, right? So,
Yeah, that's exciting. And you also received you were honored with the Presidential Early Awards award for scientists and engineers. So we are very honored having you here. And before we start, as I said, we usually start with a short interview. So if you could tell us, how did you discover that you would like to become a scientist? Was it something you always wanted to do, or was it, did that interest come later on while you were at university? If you could tell us, I think that's really interesting. Thank you.
sure. I mean, in the 70s, 80s, and 90s, the place where I grew up, science is more like, if you are smart, you do science, right? So that's what always drive people. So that's I feel in China where I grew up. That's in the 70s, 80s, 90s. That's where the big environment, and of, of course then you also get trained in that way. I think that's probably have big impact. I also is very interested in studying science in the high school. So eventually, of course, go to the universities, which basically focus on science and technologies, and then starting from there. So if you say, well, when did I actually start to get interested in science? I actually cannot really nail a time. Maybe even when I was a kid, probably I'm more analytic instead of more literature, let's put it this way. But namers like in one at one point of the time say, hey, I suddenly say, okay, this is really interests me. I want, because of this, I want to do science. I don't think that's the case. But over time, it's slowly building up. So
Yeah, that's nice that also you had the opportunity to have to be exposed to a good science curriculum. So I'm glad because now we speak and you do this really interesting work. So I'm glad that that is the case. And um, how did you choose then to go into this field of research that you are in now, physics, and then working on this project, Brookhaven Lab? If you could give us some behind the curtain speak, thank you.
sure, thank you. So when I was in college, there is a quite big group in the USTC who work in high energy, and so when I even in starting second year, I will participate in their lab work. I will set up a cosmic ray triggers testing uh, detectors for some of the experiments there. So they actually get me interested in 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 this kind of science. Then when I went to Yale, in at that time, Rick was just starting building up in '94. So Rick was start building the collaborations and detectors starting from about '93. And so Yale actually has also two professors participate in building the detectors and also running experiment at the AGS. So in the first summer, I already start working with the professor in the summer, which is actually quite interesting. So from there, I start to participate. So after qualify exams, all of this, you pass all the tests, and then I officially joined the group and doing experiment at the AGS, which is a smaller accelerators at Brookhaven. So I used to travel between New Haven and Brookhaven through the ferry, going through Port Jeff, and eventually in '99 I got my PhD from the experiment, and then moved to working at Rick. And so I have continued doing although it's one experiment, but it's a very big experiment, so I can do all kinds of different topics, and that's actually quite interesting. And I also going from, like you mentioned before, playing different roles in the collaborations all the way to the collaboration spokesperson. So from 2013 to about 2020, my main focus is the spokespersonship, running the collaborations, and only in the last 3 years I start shifting to coming back, working with postdocs, working with students on specific science topics, analysis and paper, and that's where get me here. So for this talk.
That's nice. Now you live by the ferry. You can still visit back your friends at the Yale.
Yes,
but
yeah.
yeah, thank you so much for sharing that. Sorry, I think it's always really interesting for people that are not scientists or not from the field to learn how projects and careers like come about, and yeah, and what the story is behind those papers. So thank you so much for taking the time to share that with us. And for everyone, the presentation is pinned on top of the room. Feel free to access it. And the stage is yours. Thank you.
Thank you, and thank you for inviting me to give this talk at the clubhouse. And I'm very happy to give this talk. And it's kind of new form of presentation for me. Usually we do Zooms or in person. And so, if you have any questions or things it's not clear, please remind me. For example, I should every term page I should tell you which page we are. So if it's not clear or lost track of which page you are, please let me know. So now we are going to the talk. The first slide is the title slide, and I also give you information. Usually we also post our paper in the archive, and as mentioned before, we just published the paper in Science Advances in January 4th. So if you go to Science Advances, you will be able to find that paper as well. So in the talk, I will basically trying to describe what we measure, what the method we measure, and what the results and what the future we are trying to in the future what we can do with this technique. So usually when you submit the paper to Science or Science Advance, they will ask you to have a short title and a teaser. So these are the short title and the teaser we send to the Science Advance. So the short title, other than the official title in slide 2, is quantum interference enabled nuclear tomography, and I will go into detail, explain why this is. The teaser we give to the Science Advances, we are using the polarized photons to fuse with the gluons to create a particle which then decay. In this process, it actually have the quantum wave interference of non-identical particles, and we can use this information to also measure the shape of the nuclei at very high energies. So it was one of the 3 featured articles in the Science Advance, and so the right top one is what we provided to the science. So I will also go into details what that means. So overall, within two weeks, it has been downloaded by 11,000 times, which is actually quite good. So just give you some background, right? So you probably heard in slide 3, I provided some background. You probably heard the Young's double slit experiment and the importance of the phase of wave function in quantum mechanics. So I will go into details. So more than 200 years ago, Young's experiment already demonstrated lights are like waves, right? So in wave propagations, if the lights can pass through 2 slits spontaneously or has the possibility to pass 2 slits, there will be interference patterns like waves. So you will see very intense slits on the projected wall, and then dark ones, and so it's this pattern which convinces us that lights can behave like waves. But the key point here is that the original source, the light, has to come from one single source. It has the possibilities of passing 2 holes and then that will create the interference pattern. So in slide 3, the right panel, the right picture on the right side is a more modern young slit, double slit experiment. But instead of using the light, you can actually using electrons. You have an electron gun, which has the possibility of passing two slits, and then you will create this interference patterns. Right? All this you can find from Wikipedia. Right? So the important part is to get this interference pattern, you have to have one electron gun which shooting at the slit has possibility of passing both slits. But if I design an experiment, instead of one electron beam gun, you have two, and each one can only shooting at one slit, then you won't have any interference pattern. Right? These two electron guns will, when shooting through the screen, it will behave as if they don't know each other at all. Right? And the point is, in quantum mechanics, you not only just have coordinates and momentum like a wave in the pond, or all this you can see by eye. It actually has an invisible phase in particle wave functions, and that's keep this interference pattern happen. Right? If you have two separate electron beam guns shooting at separate slits, even it's the same slits, they won't produce any interference patterns. Okay? And that's because the phase has to be in sync to be able to produce this kind of interference. So with this background, slide 4 assures our experiment the star collaborations at the relativistic heavy ion collider. The relativistic heavy ion collider is in Long Island. You can actually see from the satellite, and this is the Long Island. You can see a white circle if you zoom the area from the satellite, and that white circle is the ring of the collider. It's about 3.8 kilometers in length, and at the injection entries, this is the STAR experiment. There are 4 other experiments, and now STAR is the only operational experiment. And this is the detector. If you look at the right bottom picture, this is the detector which we actually did the experiment, and the picture was taken in 1999 before we actually rolled the detector into the hole and started the experiment. The STAR collaboration now has over 700 scientists from 14 countries. It was established in 1993 and operational since 2000, and you can see the webpage for more information. So for doing this quantum interference, you need 3 ingredients. So slide 5, I show you 3 ingredients. You need the photons to be polarized. It produces a vector mesons when interact with gluons. This makes the vector mesons polarized. You also need 2 wave functions at the distance so that these 2 vector mesons, these 2 particles are not interacting before they decay. And then you also need an entanglement between the pi plus, pi minus, which from the low decay, and then be able to interference between the pi plus itself and pi minus itself. So this on the top pictures we usually call the Feynman diagrams, which show you say, okay, ions coming through, it can emit 2 gluons, and then interact with a gamma with a light, create a vector meson we call rho, which is polarized, decay into pi plus, pi minus. But this process can also happen to another ions, and then it create a rho zero. It decay into pi plus pi minus. The pi plus, because they have different phases, they can actually interfere, and then you will create the interference pattern. So the bottom one is more looking at the picture where one of the ion coming into the screen, the other one coming out of the screen, and you look at the transverse pictures. So a light from the photon from one ion interact with the gluons in the other ion, create a vector meson, then it decays. The decay product start the interference process, but that interference only happen when the pi plus pi minus at decay are entangled. Okay, so this is another more picture look at it, right? So zoom in picture, at the surface of the ion, you create a rho, which decay immediately into pi plus pi minus. The other one also did the same thing at a 180 degree. They also decay into pi plus pi minus. And then the pi plus will come together. The wave function will interfere, create one pi plus. Then the two pi minus wave function will add it together with a phase and create pi minus. So at the end of the day, all we see in the detector, inside this detector, this actually is a real detector picture with people in 1998. They are installing the detector. You can also see we only see two particles. So all these four particles, all these decays, two laws, when we discuss about this, there are actually no a physical particle, they are actually wave functions. So although we show you two laws, but those are all wave functions, 4 pions, 2 plus, 2 minus, they actually physically they don't exist at all. It's all wave functions. At the end, all this happen, and we only detect 1 pi plus and 1 pi minus. So this has to be very clear. So when we're talking about quantum entanglement interference, they are all happening at the wave function level. It actually, in real physical particle, it actually doesn't exist. At the end, we only see 1 pi plus and 1 pi minus. Okay, this is a very, very important. And you can see the two laws, they are at distance 20 Fermi, which is much, much further away than their lifetime, so they will decay immediately. So these two laws, they actually never has any chance to interact, or even their wave function never actually overlap. They actually don't know each other at all. So all this happen, interference is only through the pi plus wave function, pi minus wave function. And when the law decay, the entanglement keep this pi plus pi minus phase at a certain phase, and it doesn't change, and it's this make the interference. Like I mentioned in slide 3, that phase is very important. Otherwise, you don't have interference if they have a random phase between each other. Right? I mean, you probably know using light to image any object that is diffractive imaging of any object has been done in many, many places. And same thing with nucleon. You can actually hit the nucleus with a high energy photons, and the diffractive pattern will tell you the size of the nucleus. So this is very similar to many, many other measurements using the cyclotron light or using the X-rays. Right? So I won't go into details in slide 7. I just show you there has been a long history of using the light to actually imaging uh, any object, right? Using the diffractive patterns, using any object, right? So I tell you there are 3 ingredients. In slide 8, I tell you the first step. How do we know the photons from these X-ray heavy ions are polarized? We actually can measure that, and this is through the famous Bragg-Wheeler process. So Bragg and Wheeler are 2 scientists predict in 1934 that 2 photons can interact with each other to create electron and positron pairs, right? And so they can actually also calculate polarizations and the angle. So not only from the process I tell you the photon from one nucleus can interact with the gluons from the other nucleus, but the 2 photons, they can also interact. And if they are polarized, they will have angular distributions. And we actually measure in slide 8, I show you this plot which published 2 years ago. It actually has the angular distributions which consistent with 100% linear polarized photons. So from that measurement, we know those photons interact with the gluons are polarized. Okay. So slide 9 shows, so now we can actually look at different angles of now coming back to the law, photon interact with gluon to create a law. We can actually calculate invariant mass of the pi plus pi minus. You will see the mass distribution of the law, and you know that's the particle which actually create all this wave function, all this interference. We can look at angular distributions, and you can clearly show these interference patterns at different directions. So there are 2 features. It has striking asymmetrical dependence of the diffraction. So because the gold ion looks like a ball, so if you don't have any interference, it should give you the pattern which that doesn't depend on the angle, right? And this already tells you something else other than a diffraction happens. So slide 10, I go into a more explanations of how this happened, right? So this is actually a normal form of quantum entanglement, and it's different from Young's double slit experiment, in which Young's double slit experiment, it actually has the photons come from one source, and it's identical photons. Photon and photon, they are identical particles. You cannot tell one from the other. What we have done is actually non-identical particles from 2 different sources actually interfere, right? So in the slide 10, the right side, the picture give you the idea that you have 2 low wave functions. They actually are not from same source. They are actually from different ions interact with different ions, create 2 wave functions. These 2 wave functions, and then it decay into pi plus pi minus, right? And then the pi plus will interfere with each other. Pi minus interfere with each other. But because originally, if it's just low, and these 2 low wave functions, they don't have a fixed phase, they have a random phase, you actually don't get this interference. So the pi plus itself won't get this interference if it's not because of the pi minus, and if it's not because the pi plus, they are from a decay, they have a fixed phase, right? So this is kind of complicated entanglement. So. Okay, so just to summarize, you need all these 3 ingredients to happen to be able to see this funny interference pattern I show you. So you need the photons to be polarized, the vector meson which it creates to be polarized. You need a two-wave function at a very large distance to actually two-wave functions. So you have decay into total of 4 particles. And then you need the entanglement between pi plus pi minus from one particle decay, so that this pi plus and pi minus they are separately can interfere, right? So these are all the 3 ingredients. So I show you the photons are polarized, the vector meson are polarized, and how do I know, say you need 2 wave functions, and we actually have a way of doing it. So this slide 12 show you, say, okay, if I have different system, for example, can have gold ion collide with gold ion, uranium collide with uranium, proton collide with gold. So in the case of proton and gold, the proton only carry charge 1, gold carry charge 79. So they are very different photon field. So the proton has much weaker photon field, so it cannot create enough photon to interact with the gold. So it's like one-sided. So you only have one wave function. And indeed, if we look at the p-gold interactions, you see nothing. There is no interference path and there is no angular distributions. But for the uranium and gold, you actually see a very dramatic angular distributions. And you can also look at their momentum distribution of this pattern as well, and you see the p gold actually consistent with 0. It means because you only have one source of the photon source, you don't have 2 to actually interfere with this. So we experimentally establish indeed you have 2 wave function which cause this interference from the entanglement. So in slide 13, I try to tell you, say, if you can look at different angles of those decay interference, and you can actually try to measure the size, and they look very different if you look at different angles. So you need to have a way. In slide 14, I tell you, looking at different angle, look at the size, then you can actually deduce very precisely the actual nuclear size. For example, the gold, what's the size? The uranium, what's the size? And this we were not able to do for the last 20 years because we didn't understand this interference effect from the entanglement. Now we understand it, we can actually use this angular distribution to extract very precisely the nuclear size. And that's very important because for the last 20 years, we are always very confused why the nucleus, if we don't look at this interference pattern, just look at the diffraction like any other people did it, you sunlight on one object, you look at the diffractive, from the diffraction pattern you will be able to measure the size. That method didn't work because we didn't take into account this entangled interference. And after we take this into account, we can actually measure the nuclear radius in terms of Fermi very precisely. And then you can actually extract this information at neutron skin and compare with other measurements at the lower energies at other places. So on slide 15, on the bottom, on the right bottom plot, which show in previous other people's publication measurements of the neutron skin. Neutron skin means the radius in the nucleus, their neutron distribution and proton distributions are different. And this is related to the symmetry energy, which actually can constrain the equation state of the neutron stars. So we can actually have independent measurements trying to see what are the equation state of neutron stars due to this asymmetry energy between the neutron-neutron interactions and proton-proton interaction. So our measurement seems to indicate like it actually has a very high neutron spin, then most of the model will predict that this will give you a stiffer equational state than expected. So we are trying to figure out where may be potentially issues and where we can measure at different nucleus and see whether we can map out this systematically and compare with other measurements. Right? So slide 17, I also come with, these are all words. We actually can build a model from other measurement, from theory, and compare with data. For example, you can have the gluon distributions, or from experiment empirically calculate the distribution and compare with data. And you can see this in slide 17, the angular distribution as a function of momentum of the particles, you can actually roughly describe the data, but there are a lot of details that don't really match. So we need to actually improve our understanding. Okay, so there are several ways to improve how to match with the data and whether that we can actually then extract more information. For example, the right top peak distributions, you have the first peak, the second peak. So the higher PT, the higher energy diffractions will tell you more detailed distribution of the nucleons, and we actually haven't going into this detail. This may give us more details about the detailed distribution of the nucleons. The other thing we can do is test fundamental quantum entanglement. Right? I told you that we create the raw particles, but there are two wave functions. Right? Similar to the double slit experiment, if we added in slide 19 on the top right, if we added some noise to the system, we then destroy the quantum interference or the entanglement. So this actually we can do. We can actually move these two ions collide to closer to each other, create a lot of particles, and see whether the entanglement still persists. So this is something in the future we can do. In slide 20, if you look in the Nobel Prize in Physics 2022, just a few months ago, in their web page, they give you a case, right? Say, you can actually create entangled particles that they actually never met. For example, in this left picture from their web page for the 2022 Nobel Prize in Physics, they give you a case, say, I have a source called pair 1 emit 2 photons, have an independent source called entangled pair 2 emit 2 green photons. These two sources, they actually have nothing to do with each other. 1 and 4, these two photons has nothing to do with each other. But if I can manage to entangle 2 and 3, you actually can create an entanglement between 1 and 4, which these two photons actually has never met, right? So in fact, I'm thinking we actually have the case which is similar. I told you about the pi plus interfere, pi minus interfere, but we actually don't know whether it's a case which is similar with this entangled particle that never met. Since pi plus, pi minus are particles and antiparticle of each other, their wave function in principle can cancel each other. So if the law from one source and law from the other source, they decay into pi plus, pi minus. If the pi plus from one source and pi minus from one source, their conditions are right, they can wave function completely cancel each other. So what you detect is particle 1 and 4, which is pi minus, pi plus. These two particles actually had never met each other, but they are actually entangled. So this is one of the cases which actually can exactly map to what's in the lab pictures, but nature actually create this for us to manipulate instead of we need the entangler to merge 2 and 3 together. So this is actually quite interesting and exciting, and we try to find whether there is a way we can actually distinguish this case and the pi plus interfere, pi minus interfere. So that's quite exciting. So in slide 21, I just summary and the future perspectives. I won't go into the details. I will be interested in see if there are questions and comments. Thank you.
Thank you so much for this really amazing presentation to explaining to us how, the advancements you made to see this in different angles, and then the groundbreaking results you got with this. So thank you, we really appreciate it. And I wanted to ask, did so you managed to have basically different angles recordings, and how did it also changed, the perspective also changed, the size that we measured before, I think, right? So before we thought, or the visualization was bigger, and now it's more accurate. By by how much is it now more accurate, and will you basically maybe even increase in the future the amount of angles you will look at this,
Yeah, very,
or
very good question. I, I skipped some of the technical details, but if you go to slide 13, and indeed, right? So, are you at slide 13?
yes, thank you.
Okay, so if you look at the 0 degree and the 90 degree, these two plots show you the extracted radius, which we call R, right? So one is 7.9 Fermi, the other one is 7.09. So they are almost different by 1 Fermi. But even this number is actually much bigger than what we actually finally extracted using this method. So if you go to slide 14, then you look at the angular distribution at different angle, right? So these are measuring at different angle, and then you can use the formula to extract the final radius. For example, for gold, which is 6.62. This is to compare with the in slide 13, 7.9 and 7.09. So they are all much bigger, right?
Yeah, so would it also, if we would do that with other particles, would we have a similar effect using your new technique?
Yes. So slide 15. That's what we measure the gold and measure the uranium. So we are trying to push, for example, whether we can measure LHC, which run that, and then we can compare with the lower energy ones. And unfortunately, we run other copper and many other systems, but some of the system, when we take the data, we don't take specifically this data, so we are not able to do the imaging. But yes, it will be important to be able to, in slide 16, I show you, to be able to actually measure other nuclei and see if they are consistent or they are in a different chain. So that's actually very important. So.
Yes, that's interesting. And do you assume that the effect you see, because the results you get, that this would be also happening with any other nuclei? As you said, you imaged this specific one. Do you think the same effect with the pions? That's that's most likely, you know, something we can generalize, right? Or
Yeah, that's a very good question. So I mentioned that specifically in our measurement law, right? So if you look at slide 6, we specifically create law, but there are no limit to law. The photon interact with the gluons, they actually can create other vector mesons. For example, phi, which will decay into K plus, K minus, the kaons, or the Jepsi, more famous particle, the Jepsi, which decay into electron and positrons. And they will have also this effect. Although their lifetimes, their spin of the products are different, so it will be slightly different numeric results, but they will all have this effect. And so in my summary slide, yeah, so if you look at 1, 2, 3, 4, the item 4 is be able to actually test all of this with other particles, right? Phi and Jepsi and other particles, and they are heavier, so they have also decay into different things, but this quantum effect should still be there. So we are very interested in future measurements, so there will be a lot more things come up.
yeah, I'm curious to see. And I know this effect, like this, is a very fast reaction, right? It's like I forgot
It's
the
like
name.
Fermi, so if you
Yeah.
want to say how many, how, the time it will be 10 to the minus 23 lifetime with seconds, right? So it's very, very fast.
So we won't. It will never be possible to freeze this in time because just thinking about maybe doing this for communication or so. I don't know if it would even be necessary or but this to have different particles being entangled, but let's say this would be something we would like to use, I don't know, between US and Australia. Would there be a possibility to basically freeze this in time and then yeah,
Yeah,
I don't know, probably it doesn't make sense.
probably using this kind, it's probably not effective. Also, pions decay as well, right? But like in my slide 19, slide 20, what we can do is test some of the, the fundamental features of quantum mechanics and entanglement, and that will help others, may be able to help others to actually build communication systems of computing. What we can do is using these kind of systems to test fundamental quantum mechanics and quantum entanglement, right? For example, slide 19, right? One of the issues is if you add noise into the system, will you be able to still maintain that information, right? That's very important in quantum computing and quantum entanglement communications. So what we can do is testing this. If you add a noise at the fundamental level, does it actually destroy the entanglement, right? Slide 20 tell you we can test whether we don't need an entangler. Slide 20, you actually have the wave function built in the nature that actually can actually cancel each other, right? So these are more testing the fundamental features of quantum mechanics, the phase of the wave functions and the entanglement. And this may help other people building, like you said, communications at the, give you a foundations instead of say using what we have to build a big system. I don't know whether this make it
Yeah,
makes sense
yes,
to you. So
yes,
okay.
it does. Thank you so much. This is really fascinating. And so you said there wouldn't be needed maybe entangler, and we still need, or you would need to test if this effect is also being seen with noise. And assuming with adding noise, it would still, different type of particles could become entangled. Um, it's really interesting to think. So, do you think there's interpretation for like the macroscopic world in this experiment that
Yeah, that's right. So that's a very good question. For example, we are talking about the quantum computing communication with entanglement. So one of the issues is if you have noise, if you have vibrations, if you add noise from the environment, will they be able to still contain the information, not just lost it, right? So this will be also one of the tests, right? At the very wave function level, fundamental level, if I add a noise to the system, with a wave function certainly collapse, and the pi plus, pi minus from the low decay, they don't maintain, they entangle information, their phase, right? So this is something we can test in the future.
Thank you so much. I wanted to give Kirko an opportunity if he would like to ask a question, and also everyone in the audience. Please feel free to raise your hand and ask a question here on stage, or leave a comment or question in the chat. And yeah, Kirko, if you have a question, go ahead.
Give me a second. I got to kind of think about like all of this. It's pretty cool talk, but I'm not gonna lie, I'm kind of lost. So give me a couple minutes to get my thoughts together.
Sure. Yeah, it took me more than 2 years to actually think this through and how this can happen, and what happened, what we can test, what improve. So even for us, it's actually quite new, and it took us a long time. During pandemic, we have all the time to think through, and I think that actually helped, to be honest. Think through for 2 years to actually go through all of this, and at the beginning we are all very confused too. So
That's interesting and comforting to hear that. So were people really surprised, your colleagues, when they heard the results of your experiment? Um, what and how often did you have to kind of repeat it, that you believed yourself, and yeah.
yeah, I mean, in the general terms, hey, this is very cool. We can prove there is entanglement, and at the distance level, people think, okay, that's possible. But if you go into the details, not many people actually understand what we are actually doing. Even last week when Daniel was giving the colloquium, and a very good friends and also a very established and quite famous scientist in our field, theorist, he told us he finally understand what actually we were doing. So it's yeah. So it's, I would say it's a highly non-trivial and complicated, but at the distance, right? It's easy to understand. Say, hey, I have wave functions, I have entanglement, and this enables us to actually very precisely image the nucleus using this technique, and we achieve this by looking at non-identical particles entanglement. Right? So at the distance level, it's the concept seems to be understandable, but in the detail, how it was done, what's involved, I would say, even now, not many people actually in the field actually know the detail exactly how it works. And even in slide 20, right, I just give you examples that we are even not sure whether this is the case or the other one is the case, right? So
Yeah, so yeah, I think it's really interesting that when I read that the pions, that they carry the information from their originating particle, and that in this short time they exist in a very short time. They can basically communicate the information from their originating particle in that short time. I feel that is very fascinating to me and very puzzling, and this microscopic, very short time world, you still have this, yeah, you still have this effective way of yeah of information transfer. I think that's really interesting. Is that the limit? Basically, information can be transferred on this level, or do you think there will be even one day shorter wave functions with even shorter time that we will discover that can still transfer information effectively?
yeah, so you that's right. So in slide 3, I mentioned a very important concept, and like you said, that information is embedded in this called phase, right? So ordinarily, if you just measure the particles where it is and what are the energy or momentum of that particle, that information actually get lost, right? So the only thing it embedded is say these pions somehow it will interfere with other pion wave function from the other law and create this interference patterns. So one of the things, if you go to the final slide summary, is, as I mentioned before, we can use different particles. For example, phi and j psi, they are heavier. That means they can be more localized. So indeed, if, for example, the photon energy to create phi and j psi will be higher energies, so we can do shorter distances. And so that's one of the things we want to do, and we will see what the outcome is. So this, you are exactly right. So we are going to try to use heavier particles, higher energy photons to see, and also if you use different nuclei, you can actually control also the distance, how close they can be, or how far away they can be.
Oh, that's fascinating. I'm curious to learn about your future research. Einar joined the stage. Welcome, Einar. I hope do you still have a couple of minutes to answer the
Sure,
question?
sure.
Thank you. Go. Hey, Einar, go ahead.
Yeah, hi, Katarina. Thank you very much. Hi, Shangbo Shu, if I said your name correctly.
Perfect.
Um, so, what I'm wondering about is that I try to see in your on the document here, as Katarina mentioned, like the angles might not be would be simplified. But my question is that if there actually is an entanglement or not, um, do you, what are your thoughts, and or do you have any speculation what kind of wave functional force actually being involved when it comes to entanglement or not? Like, is this something you can say something about? Thank you.
Yeah, so very good question. So in slide 3, I tell you, say, what you need, right? So very importantly in quantum mechanics, all this entanglement or happen is you either have to have the somewhere create a correlation or a phase which embedded into this particle's wave function. Right? So in slide 3, on the right hand side, I give you an example. Say the electron beam gun going through two slits can go through two slits, you create interference pattern. The reason it can create that interference pattern because the electrons come from the same source, so their phase, when they pass through slit 1 or pass through slit 2, this two-wave function has exactly the same phase. So that when these two wave functions going through, they will have a phase which create fixed phase which create interference pattern. If I have two separate electron guns run by two different people shooting at one slit each, you will never create this pattern because this two-wave function has a random phase. So we know these two guns, and people did explain these two guns, if you don't have these two sources of electrons, they are not in any way entangled or correlated, you won't be able to create the interference pattern, right? And we also have a case. If you look at slide 12, we use a proton gold, which you only have one source. You also won't create this interference pattern. It's absolutely zero, right? So we know that you do need two wave functions, and you do need entanglement to actually create any of these patterns we observed. I don't know whether that answers your question.
Oh, yeah, it answers a lot. But and I just a follow question here. Is it can you see a relation between more dense solid matter and what's not dense solid matter in like a physical way, or?
Good, that's a very good question. So slide 12 answered some of that question, right? If you look at the uranium and gold, right, they actually have different size, and we actually can see they have different patterns, right? So the red is the gold, the black is the uranium, and you can see I didn't tell. So you see on the right hand side plot, you see the black and the red both has one peak, but they actually going down in a different way. And when you go to higher, we call PT, you actually have different patterns. And this different pattern probably tell you different internal density of these two objects. And we haven't gone into the detail of the second peak, third peak, all of this. So if we have, in the future, if we have enough statistics, you will be able to actually see a more detailed distributions inside. But just from this, probably you already see uranium and gold, they have different size, and you do see different results, right?
Ah, thank you very much. Thank you. Yeah.
Well, yeah, we went a little bit over an hour, but this is such a interesting topic and such a fundamental research. So that's really interesting. And thank you so much for explaining this to us in a way that we are able to ask some questions. I hope it was okay. And I hope you enjoyed the discussion a little bit too. And I'm
Yeah.
very curious to learn about the future, results you will have with different kind of particles and and figuring out the distance between the wave functions so they can entangle. So it's really interesting. It's fascinating. Thank you.
Yeah, we have different groups working on this, so I'm expecting in the next few years there will be quite a few different results related to this topics come out. So, and thank you very much. It's really a pleasure to discuss and communicate with this group about this topic. So.
Yes, thank you. And yeah, maybe we hear you back one day. That will be exciting. And yeah, I hope everything goes well with building a new particle collider in the future. I know it's still years away,
Yeah, it
but
will be usually it take about more than 10 years to build one, and then it take another 20 more than 20 years. So the first the relativistic heavy ion collider, the first proposal was in 1983. When it started proposing in 1993, we start building a detector. In 2000, we started running. So now we published this paper. It's like 23 years later after the first operations. Compared with 1983, it's 40 years before we, from starting proposing to actually have these results. It's 40 years. Probably quite many of you probably have not been born at that time yet. So, uh, so it's a fascinating phenomena, I would say.
oh, that's interesting. Thank you for sharing that timeline with us. I wasn't aware of that. And I mean, I'm glad that we have places in the world where people are still patient to wait, to invest money and wait for results, because I feel like in the last maybe 20 years, we kind of always focus more to applied science and having fast papers. So I'm glad to hear, so we can learn about how our universe works and not focus on producing papers and papers that don't, bring anything groundbreaking. So I'm glad, and thank you for sharing all this information, giving us a peek into behind the curtains, how things work and what the timelines are. That's really interesting. So I hope you enjoy the rest of your day, and yeah, good luck for everything in the future, and we will keep following your work. Thank you.
Thank you. Same to you and everyone. Thank you.
And yeah, everyone, thank you for coming and asking questions. It makes the discussion so much more interesting if more people ask questions from different perspectives. And the next talk will be with Dr. Taverna, talking about polarized X-rays from magnetars. So yeah, kind of interesting discussions this week that I have to study a lot for.
That's also a very interesting topic, which is related to us, the polarized photons, right? So,
Oh, maybe you want to come. The talk is
yes,
tomorrow at 9 a.m.
I see. Okay.
Yeah, I can send you the link if you would like to come. It'll
Okay.
be for sure interesting discussion if you're there too.
Okay. Thank you.
Okay, great. Thank you so much. I'll close the room in 3, 2, 1. Bye, everyone. Thank you.
Bye.